Hello everyone, this is a video I made for my Thermodynamics 1 course, ENGR 251 at Concordia University on the topic of the ideal gas equation of state. My name is Emil Kolasinak, and in this video I'm going to try to go over some of the theory that's related to the ideal gas equation, and at the end I will try to solve one problem to demonstrate the application of this relation. So let's get started with a definition. What is an equation of state? So any equation that relates the pressure, temperature, and volume of a substance is an equation of state. Some equations involve other properties of a substance at equilibrium states. So these relations are also equations of state. So we don't necessarily have to have pressure, temperature, and volume. We can have other properties in an equation, and those equations are also considered equations of state. Now some are simple, others can be complex. The simplest and most common equation of state is the ideal gas equation of state. So this equation predicts the PVT behavior of a gas accurately under specific circumstances. So here we see two forms of the ideal gas equation of state: PV equals MRT and PV equals RT. In the first one we have the total volume V, in the second one we have the specific volume V, and we also note that in the first one we have the mass on the right hand side of the equation, but in the second equation we don't have the mass. So when can we use the ideal gas relation? Can we always use it? And the answer is no, we can't always use it. Certain conditions have to be met. So those conditions are that we need to have low density, meaning low pressure and high temperature, and then we can use the ideal gas relation. Now, what does it mean to have low pressure and high temperature? It means low pressure with respect to the critical pressure of the substance, or high temperature, again, with respect to the critical temperature of the substance. So for gases, it has been observed that at low densities, when we have low pressure and high temperature, the pressure under these conditions is directly proportional to the temperature and inversely proportional to the specific volume. And we can see from the first equation that the pressure and the temperature are on the opposite sides of the equation. So they are directly proportional. Increasing the temperature will increase the pressure. Decreasing the temperature will decrease the pressure. Now if we take that same equation and we rewrite it in the second form here as PV equals RT, because it's essentially the same equation, it's just that it has the variables rearranged. So now we can see that the pressure and the specific volume are on the same side of the equation, so they're inversely proportional, which means that if I increase the volume, I will decrease the pressure, and if I decrease the volume, I will increase the pressure. So under these circumstances, low pressure, high temperature, we can use the ideal gas equation of state. So in its simplest form, PV equals RT. In this equation, P is the absolute pressure, so we can't use the atmospheric pressure, we can't use gauge pressure, we can't use values for vacuum pressure. It has to be the absolute pressure. The temperature has to be the absolute temperature in Kelvin. V is the specific volume, and R is a gas constant that is specific for each gas. Each gas has its own R constant, which has to be, we usually get them from a table. We just read them from a table. Now, how is a gas constant determined? Well, if there's something called a universal gas constant, which is a gas constant that is the same for all gases. And if we take that constant and we divide it by the molar mass of the gas that we're working with, then we get the specific gas constant. So that's how that's calculated. And the universal gas constant is, of course, same for all substances. It has a value of 8.31447 kilojoules per kilomole Kelvin in the SI system. In the imperial system, it has a different value, but we're working with the SI system. So the ideal gas relation can have different forms. Here in red we see PV equals RT, and we also see that the specific volume V is equal to capital V over M, and if we plug that into the first equation, PV equals RT, then we get PV over M is equal to RT, and then we can just move M on the other side and we get PV equals MRT. So that's how we go from PV equals RT to PV equals MRT. And in black we have two other equations that use M molar mass and they use N, which is Avogadro's number, and the equation looks slightly different, but it just takes some algebraic manipulation, and they can easily be these equations can easily be obtained. In the last one over here we see V bar. V bar is for molar specific volume. So again, the specific volume expressed in moles per in cubic meters per mole, if I'm not mistaken, as opposed to cubic meters per kilogram. So we are, for the purpose of this video, we're going to use PV equals RT and PV equals MRT, and most of the time you will be using these equations. The two equations on the bottom are not used as often as the others. Now, a note: an ideal gas is an imaginary substance that obeys the relation PV equals RT. So an ideal gas actually does not exist. It's a concept, and the real gases sometimes, under given conditions, can approach the behavior of an ideal gas, but they can never actually behave as an ideal gas. It's just not possible. So most of the gases that we're working with in problems can be treated as ideal gases: air, nitrogen, helium, carbon dioxide, etc. However, water vapor should not be treated as an ideal gas, and refrigerant vapor should also not be treated as an ideal gas. If we have a problem where we're dealing with these two substances, we have to use the property tables in order to determine whatever we are asked to find. So with that being said, let's try to solve a problem. Let's see the ideal gas law in action. So this problem says that the pressure in an automobile tire depends on the temperature of the air in the tire. When the air temperature is 25 degrees Celsius, the pressure gauge reads 210 kPa. Now we have to be careful here because first of all, we want to change the temperature that's given in Celsius to Kelvin right away, because well, that reduces the possibility that we're going to forget to do that, and to use this equation of state, we always have to use absolute pressure, absolute temperature, and so on. So I would change that to Kelvin right away, and then the pressure gauge reads 210 kPa. So pressure gauges are calibrated to read 0 at atmospheric pressure. So when we read 210 kPa, we're reading gauge pressure. But we need the absolute pressure, and the absolute pressure is the gauge pressure plus the atmospheric pressure. And the gauge pressure is 210, and if you read the last sentence of the problem, it says assume the atmospheric pressure is 100 kPa, so 100 plus 210 is 310 kPa, and that's our absolute pressure. If the volume of the tire is 0.025 cubic meters, so that's the volume is given, and the volume is, we're going to assume that the volume does not change. The tire is not going to expand just because it heats up, so the volume will remain constant. So that would be the volume, and if the volume is 0.025, determine the pressure rise in the tire. So in other words, find P2 when the air temperature in the tire rises to 50 degrees Celsius. So that would be T2, which is 50 degrees C, or 323 Kelvin. Also, determine the determine the amount of air that must be bled off to restore pressure to its original value at this temperature. So the amount of air that must be removed. Now, let's see how this is done. So, first we're going to focus on the pressure. We want to solve for the pressure, and then we'll deal with the mass. So for the pressure, we're just going to write the ideal gas equation for the state of the system. At state 1, P1V1 equals mRT1, and then we isolate the mass. And then at state 2, we have P2V2 equals mRT2, and we isolate the mass again. Now we have to be careful. We have to note that the mass of air is not going to change. It will change at the end when we remove some of the air, but for the time being, as we're calculating the pressure, the mass of air is not going to change. So these two expressions are the same. So if we equate the two sides, we get P1V1 over RT1 and P2V2 over RT2. However, R is a constant and it has the same value, so we can remove it from both sides of the equation, and we said that the volume is constant, it's not going to change, so we can get rid of the volume. So we get this expression, P1 over T1 is equal to P2 over T2, and then we can simply isolate P2 and solve for it. If we plug in the numbers, we get 336 kilopascals for the pressure. So that's the pressure, and now let's focus on the mass. So initially, at the beginning, the mass that we have is found by using this formula. These are the values that we have at state 1. So we have the pressure and the volume, and this is the gas constant for air, so that's R, and then of course we have the temperature. So by plugging in the values, we get 0.0906 kilograms of air at the beginning. At state 2, we're also going to have the same mass of air. However, we want to know what is the amount of air that must be removed to restore pressure to its original value of 310 kPa, but at this temperature. When they say at this temperature, they're referring to temperature 2, 323. So we want to create conditions where, so this is what we want. We want a pressure of 310, but we don't want temperature 1, we want temperature 2, which is 323. The volume is not going to change, and the R constant is just read from a table. So if we are going to create those conditions, we're going to have to calculate what the mass would be in order to have those conditions. So then we just plug in these parameters into the equation. Again, we isolate the mass, of course, and then we plug in the parameters, and we get 0.0836 kilograms. Now, so if we initially had 0.0906, but we want to have 0.0836, we have to remove some air. How much air do we have to remove? We simply find the difference between the two, and the answer is 0.0070 kilograms. Now, one final note regarding units, just in case, if you're wondering how I cancel out the units, and this is a very good practice because you can check whether your answer makes sense or not. I do this on the side on a piece of paper usually. So I will take the units that are all of the units that are given in this equation. So I'll take pascals, for example, and I know that pascals over here, I know that's Newton over meter squared, and then I'm multiplying that by cubic meters. So I'm canceling out these two and these two, and I get Newton meters, but Newton meters are joules. And then on the bottom I have Kelvin canceling Kelvin, and I have divided by joules per kilogram, but that's the same as joules times kilograms over joules. So the joules cancel out and I get kilograms. And it makes sense because the unit for mass is kilograms. If I had gotten something else like joules or I don't know, pascals, then I would know that my answer doesn't make any sense because it has to be in kilograms. So yeah, that's how I deal with the units. Thank you for watching.